Hello, and welcome to this Deakin Alumni webinar presented by Professor Wendy Timms, Professor of Environmental Engineering at Deakin University. Zizi Moscow here from the Deakin Alumni Relations team. It's great to have you with us. I'd like to start by acknowledging the traditional owners of the land from which we're broadcasting today, the Wadawurrung people of the Kulin Nations, and to pay our respects to their elders past, present, and emerging. Today, we're broadcasting from Deakin's Warren Ponds campus, and our webinar topic is Going Looney, How the Sun, Moon, and Other Things Affect Underground Water Levels. To watch past webinar and seminar recordings, visit the Webinar and Resources page on the Deakin Alumni website. Today's webinar will be recorded and posted online and will be available in approximately 3 weeks under the Faculty of Science, Engineering and Built Environment section of the page. Before we get started, we'd love if you could share with us what drew you to today's webinar. Your microphone is muted, but you can communicate with us via the question box that should appear in a panel on your screen. Let's test that panel out now. If you could please type in which category on the screen most aligns with what drew you here today, it will give us a better understanding of why you've joined the webinar. Please type either A for working in this field, B for just interested in this topic, C for other, and please specify briefly. I'll give you a few moments. All right, so we've got a few people working in this field. Our presentation will run for about 40 minutes, followed by a discussion session with Wendy. Throughout the presentation, if you have any questions, please type them into the question box and submit. And we will go through as many questions as possible during the discussion time at the end. For those who have just joined the session, welcome to the Deakin Alumni webinar with presenter Professor Wendy Timms, titled Webinar Invitation Going Looney, How the Sun, Moon and Other Things Affect Underground Water Levels. Now it's my pleasure to introduce our presenter. Professor Wendy Timms is an environmental engineer and hydrologist with over 26 years of professional experience in government, consulting, engineering and research across both mining and agriculture. She is Professor of Environmental Engineering at Deakin University and is currently leading research in water and energy nexus, groundwater hydrology and water traces, and influence of water on geotechnical behaviour of earth materials. Prior to this, Wendy was Director of Postgraduate Studies at UNSW School of Mineral Resources and Energy, affiliated with the Connected Waters Initiative and Australian Centre for Sustainable Mining Practices. She was a founding chief investigator in the National Centre for Groundwater Research and Training. She has published over 200 technical reports and over 45 journal publications. Wendy is an active member of Engineers Australia and a vice president of the International Association of Hydrologists, Australasia Pacific. Wendy is also an invited member of expert independent panels providing technical advice to the Federal Minister of Environment and an energy on water and environmental aspects of coal, seam, gas, coal and uranium mines. Thank you so much for joining us today, Wendy.
Thank you. Thank you so much, everybody, for joining this webinar. It's fabulous to have alumni join us and others for this special session. And thank you so much to Zizi for introductions. I really appreciate that. And you know, if we've got any burning questions on the way through, we're happy for you to type in your questions. But otherwise, yeah, we'll have a good question and answer session towards the end. So yeah, just if you've got any burning questions, happy to interact a little on the way through. So thank you so much. I gather a lot of you are working in this area with water and perhaps with underground engineering projects, which is really terrific. So I think there's going to be some really excellent questions. I've put a little bit of a provocative title there about going loony, how the sun and moon affects things. And to be honest, if I'd have seen a engineering presentation with that kind of title, perhaps even 10 years ago, or certainly as a student, I would have kind of thought, well, sounds like the professors are going loony. Is this really practical kind of stuff, what we need to know as engineers? And I hope I'll give you a little bit of a flavour and how these techniques might be useful. But it's really a bit of an introductory session around all the different kind of complicated factors that influence how water underground goes up and down. So, of course, it's not just the sun and moon. You've seen probably the summary of this session. I won't kind of go through that again at this point, except to say that hopefully we'll cover off on a lot of this as time goes. But really to say that, water is such a valuable asset, and water also intersects with many of the engineering projects, as you would know, that we get involved in building infrastructure, in tunnelling, in basements of large buildings, and of course, particularly around the southwest of Victoria, the greater Melbourne area, a lot of us are very much dependent on groundwater for our water supplies, particularly during the drought. So it's not just across Australia, but also globally, bring in some examples as well. So my background as an engineer is pretty varied, actually. Here's just a few little snapshots from the last 25 years or so. I started out as a geologist working on drill rigs, and was really lucky to work in some pretty nice places, and also some pretty challenging places around the world. I worked in Canada for a while. Here I am on the top left at a uranium mine right up in the north of Canada, where the sun hardly ever set, and we were dodging bears and dodging wolves on site. I've also worked at -30, this drilling rig down here at a potash mine, where you can see we're pretty rugged up. But I love going underground and getting involved in projects, whether it's civil tunnelling or, in this case, an underground mine near Sydney. And I've also been really lucky to work in the outback on water supply and around the Sydney catchment area, and quite a few visits, to lots of places around the world, and have actually been involved in work at refugee camps early on in my story as well. I think one of the privileges of being an engineer, actually, and particularly being a specialist in underground water, has been the opportunity to visit many, many different sites in many countries around the world, and go to a lot of mines and go to a lot of project sites. So, you've heard a little bit of my professional background, and some of the work that I get involved with for the Federal Minister of Environment on expert boards. But I'd also like to share with you that, since I joined Deakin University about a year or so ago, that I've been very busy working on the new waste engineering unit for our environmental engineers and our civil engineers. I'm involved in teaching units on water engineering and geotechnical engineering, and I'm also the course director for Masters of Engineering. So we've got a growing number of master's students coming through our school, and quite a lot of different research projects going on. And the topic of today on going loony is part of the research that we're doing. So you'd be very aware, working in water and engineering, that sometimes we really have some surprises that come up. We've had some pretty big cities around the world coming very, very close to running out of water, whether it be Cape Town, whether it be Chennai in India, where water supplies reach zero perhaps far quicker than what water planning had allowed for. Even here in the Murray-Darling Basin, barely a day goes by, of course, when this is not in the media in some way. And we're seeing rivers going dry in places where we know from the age of the fish that even in some of the last big droughts, millennial drought, that never happened. So quite a few surprises, which we kind of is a little bit disconcerting as an engineer, because we think we like to control the world and we think we're on top of everything and we know all the uncertainties that we're dealing with, and that our tests and our monitoring and our modelling are all reliable. However, you know, whether it's these pictures on the bottom left here of wetlands drying, this photo here is from an upland swamp in the Sydney area that was unexpectedly affected by deep underground mining, more than 300 metres below ground. The next photo there from a bore field closer to home here to the Deakin campus, where again, a few surprises needing to really change the behaviour, the operation of these bore fields. And of course, the many towns in New South Wales that are currently on the verge of running out of water and who are frantically doing geophysical surveys, doing work to try and drill for groundwater when the dams are approaching empty. So this is I think the mayor of one of the towns, who was so excited when the drill rig struck water that he's got this wonderful business shirt with "We found water" on it, which is quite exciting for them apparently. And it would be. I mean, look, water is so critical. I've lived in some of these inland towns, and I've been involved in projects out at Broken Hill, for example, where water is just so critical an issue. So, I mean, just some really kind of groundwater 101 stuff here, just so that we're all on the one page, I guess, that we think we've got a lot of water on this planet. A lot of it's ocean, a lot of it's ice, but groundwater is really the world's largest accessible source of fresh water for our human needs. Groundwater is a third of our water use in Australia, and the general trend is upwards, particularly as you see with the drought and water deficits hitting in particularly the northern Murray-Darling Basin at the moment. So we're seeing more and more bores being drilled, more groundwater being accessed, and indeed in Western Victoria, where groundwater is on average 60% of our water use. So whether it's windmills, whether it's the famous Hepburn Springs here, and in fact you can see the discharge of groundwater seeping from the top of that spring into the local creek because of the colouring of the water. And of course that's the dissolved iron in the groundwater that as soon as it comes into contact with oxygen on the surface, it leaves this telltale brown staining, which is quite natural, but it's really an indication of a groundwater seepage. There's also, of course, lots of shallow wells that we rely on, say in the Perth area, in parts of Sydney, around the Botany Sand Aquifer, and in many areas of Asia where hand pumping wells, and indeed Africa and elsewhere, where this is the only source of water supply for the local village. And certainly the village that I lived in for a year, up in northwest of Thailand, was very much dependent during the dry season for months and months on a hand well. And pretty critical that these remain usable, that the water quality is good, and that the water table remains reachable by these systems. Then we have the really deeper, much deeper groundwater systems that are under pressure. This photo here is of a bore out in the Great Artesian Basin, out in southwest Queensland near Thargomindah actually, and you can see this one has been piped to supply the local stock and is under so much pressure that when you release the valve a bit, it shoots up many metres in the air, which is pretty exciting. But all this groundwater that's underneath the ground there, you know, it's stored within small pores, within the sand, within the rock, It could be within the fractures or the micropores within the rock. And when we're first drilling down through these layers, sediments, rock, the first saturated zone that we reach there is what we call the water table. So this is all a bit 101 stuff, but I think it's really really interesting just to kind of revisit, I think, some of the basics here. So the unsaturated zone, the saturated zone, and the water table. And of course, you no doubt know that it can get way, way more complicated than this, with perched aquifers and unconfined aquifers, confined aquifers, and so forth. So around the globe, groundwater is declining, and this map here that shows the areas of aquifers where the stresses are beyond what the recharge or the water sources into the aquifers are, you can see that the redder the colour, the more stressed it is. So particularly these areas in central the US, California. I worked up here in Canada in the Williston Basin, and then parts of the Middle East, and this big red area across Pakistan and India, the Indus, the Ganges basins, and then up into the northeast of China. Interestingly, in Australia, the GAB shows up here, and also the Canning Basin in Western Australia. I've just returned from a trip to Delhi with Deakin. We were presenting at a water summit there, and I've been to India several times over the years, and it's really quite critical that the groundwater is being drawn down many tens of metres, and it's a real concern in this part of India because so many people, so much irrigated agriculture depends on groundwater. So I think we've got some real challenges already, very, very critical situations in parts of India. This doesn't even show Chennai, which is down here on the coast where they're very nearly running out of water. So we have a few partnerships around India where we're working with them, and also on research projects and training projects. There's a huge amount of expertise across many of these areas. My role with the International Association of Hydrogeologists, and we work very closely with our colleagues across these parts of Asia where groundwater is in a bit of a critical state. In Australia, the groundwater resources across the nation are very variable, and so whether we're dealing with porous aquifers like these blue colours across the Great Artesian Basin, or indeed through much of the Murray-Darling Basin down closer to where we are at Deakin, we know the more arid the environment, the more groundwater is relied upon. And many of these paleo channels, or these old buried channels in the inland of Australia, are very, very important resources. You may be aware that many of the inland towns and mining camps and so forth rely on bore fields that are into the buried old river channels, paleo channels in the inland of Australia. On the right-hand side there, we've got a snapshot of some of the trends of groundwater levels. This is thanks to the Bureau of Meteorology and their InSight database. You can jump onto that website and you can zoom in on any aquifer or any area of Australia and timescale that you're interested in. The one that I happened to have grabbed here the other day is for the upper aquifers from a period. The longest I could choose here was 1998 through to 2018. And so this is for the uppermost aquifer in any one of these basins. So for instance, up here on the top right, we've got the Namoy catchment right up in the northern Murray-Darling Basin. We've got the Latrobe Valley down here in Victoria and so forth. And you can kind of see, I guess from eyeballing this, that many of these sites are declining over that longer period of time. Now, obviously, it's going to depend on which section of time you choose, whether it was during the millennial drought, when things would have been even worse. But trying to get a sense of the really, really long-term picture of whether water levels tend to be going up or down or are stable. There's many areas that are stable, which is good, I guess, for the sustainable long-term use, that we really in some ways want to ensure that these water resources are there when we really need them the most during drought periods, and perhaps try and not rely too much on them during wetter periods. So a little section here from the top of ground through a schematic of a water bore, or what we might call a groundwater monitoring bore or piezometer, where we've got a water level that we observe in the casing. We can put in a logger there, we can put a special dip meter down to measure where this is, but it might be measuring water that's coming up under pressure through the casing. So the casing, there's a little picture there on the left of a bit of a higher yield casing where all these slots allow the water to come in from the sediment and the rock, and they come into the casing of the bore, and then it'll rise up under pressure above the level of where that top of casing is. So that's where we know we've got an aquifer that's confined, it's under pressure. And so the head that we've got here, where we measure it relative to an elevation, so we might say it's 300 metres above sea level, above Australian height datum, we can then compare that to other locations and other aquifers and get an idea of where groundwater might potentially move. But, you know, if this water level is within the casing depth, perhaps if this casing is a bit shorter and the slotted casing is a bit shallower here, then it might actually be measuring that water table, that point at which we go from unsaturated to saturated. And I'm not going to get into kind of the complications here of some of the different perched aquifers where it kind of gets a bit more complex. But essentially, so the water level will go up and down, and we tell the potential groundwater flow direction from the difference in the hydraulic head, the elevation measured to a datum, at different locations, and assuming that it's in the same aquifer that you're making these comparisons, then you can probably assume that you're going to have some kind of groundwater flow there that's following the direction of the hydraulic gradient. The water flows from high pressure to low pressure, from high head to low head. So in this simple example, from the left to the right. Now, how fast it moves, you're going to need to know some other things like the hydraulic conductivity or the permeability of that material, what your flow rate is, the actual velocity of the water. You're going to need to know some porosity. There's all sorts of other complications, all sorts of other details that we get into in groundwater engineering. But I guess the main message at this point is that the water levels can go up and down, and it's the level of those water levels, the hydraulic head, and the relative measures of those over a distance that really determines which direction that flow can occur. So to kind of try and put a whole heap of stuff on one page, why do the water levels go up and down in a well or a bore? So you've got a whole bunch of natural influences, which you can already tell. A lack of rainfall recharge, the groundwater level will go down. Where you increase the rainfall recharge, how much water is infiltrating through that soil, down into the water table, down into the aquifer, then the water level will go up. Then if that groundwater is discharging somewhere to the surface, perhaps into a creek or a river to keep that flowing, then the groundwater level will drop down over time as that discharge occurs. And then you've got some other factors here. So then you've got the change of loading in your soil moisture, perhaps the weighting pressing down on a confined aquifer, so that kind of can make the pressure change as well. And then, and this is kind of where this talk is kind of focusing a little more, is those sun and moon cycles. So we'll come back to that one. But how much does the groundwater level go up and down, and how quickly does it go up and down? So we'll look through some examples and highlight some of these quantities. Then, of course, you've got human influences. So if you're pumping the groundwater for a water supply, or you're pumping the groundwater to dewater a quarry so that you can continue to extract some road-based materials or mine some gold or what have you. Even changing land use. And I think one of the things that we've kind of overlooked a little bit in Australia is how much we've actually changed our groundwater systems and our river and lake systems just by changing the land use and clearing trees. Every tree around the place is a pump of groundwater to some extent or another, a mini pump. So we can also change surface water flows, which influence groundwater underneath. So, for example, with a dam, and even the weighting of the water in a dam can affect a groundwater pressure. So lots of different things going on. You can see as to why water levels will go up and down. It can be kind of complicated because there's so many different influences, both natural and human. Okay, so here's an example of rainfall and the recharge influence on aquifers. And the atlas for groundwater in Western Victoria, you can see the link there down below. It's a fantastic resource, and you'll notice some of the schematics come from that. So here we've got an example from the Hawkesdale area of an unconfined upper aquifer, and the rainfall is in yellow-orange, and the groundwater level is in that pinky red. And so the groundwater level there is varying quite a lot, several metres, pretty quickly after each major rainfall, quarterly by quarterly. So you can see there's quite a pretty strong relationship there between when it rains, the groundwater levels go up. And the little schematic there on the right-hand side shows some of these hydrological relationships with the recharge getting in. And of course, if the water table's close to tree roots, it'll be used through evapotranspiration, and you'll have some discharge to form base flow for rivers, and you might have some inter-aquifer leakage as well going on. But overall there, to give you a sense of how much the water levels go up and down, they're roughly 5 metres or so each year in that location. A contrast to that, down below here, is a confined aquifer system. So this is where the groundwater is under pressure, and that's because there's a layer of clay or rock that's pretty tight permeability sitting on top of it. And so it's not immediately accessible for recharge and through to the ground surface. So here there's not such a strong relationship at all between rainfall recharge and the groundwater level. And in fact, the groundwater level is really only fluctuating there at a relatively small amount. Here's an example now with a human influence where the groundwater is going down during pumping. And this is from one of the drought supplies for the Greater Geelong area, and courtesy of the Barwon Water Report here that's referenced. And it shows a hydrograph here on the right where during these greeny areas here that are a bit faint, I hope you can see it, that's the period of groundwater operation where the groundwater levels are being drawn down, and then after the pumps are turned off, you've got a recovery here in some of the aquifers. Some of the aquifers here aren't being affected at all, or to a very small amount over a longer period of time. So from the 1997 through to 2018 here, one of these aquifers with perhaps a bit of a long-term small drawdown. But when you look at it on a map for each different aquifer layer, you'll see a different pattern, spatial pattern, of how the groundwater is drawn down in space. Okay, just at one point in time, this snapshot on the left showing kind of a bit of a bullseye pattern around where most of the groundwater pumping is happening. And it's probably a bit small to read there, but it's about -15. So there's about a 15-metre drawdown in that aquifer centred around where the groundwater is coming out. So the pattern there is going to be variable depending on the geology and so forth. But just one really good example of how groundwater is responding over, you can see quite a lot of change there, 15 metres. And in fact, some of the aquifers I've worked in, it could be 100 or 200 metres. So, yeah. The next thing here is looking at ocean tides in aquifers near the coast. And we're very familiar with ocean tides coming and going, with the influence of the moon and also a bit by the sun, even though the sun's further away. Both of these celestial bodies have a gravitational effect that we see very clearly in the tides around the planet. And so if we dig a hole in the beach sand, we can see there our water table, essentially, the first surface of water that's saturated as we go down through that beach sediment. And that will go up and down in stereo, I guess, with the ocean. Now, as you go further and further away from the land, of course, that variation gets less and less. And we've got mathematical relationships to estimate the time and the space. But generally, you know, depending on which part of the planet you're on and all sorts of other factors, the groundwater level can go up and down by centimetres or metres over hours, right? So it's not as big as, say, groundwater pumping in many locations, but that's certainly a natural influence. So if you go further away from the coast, where there is no ocean tide, the amazing thing is that we still have a tidal effect, which we call the earth tide. And so this is where the sun and the moon and also atmospheric pressure can affect our groundwater levels going up and down. So the earth tide, we can compute that just like we can compute or predict our ocean tides, so we know when to go fishing or what have you. But with our earth tides, exactly the same kind of process, that we've got the gravitational influence of the sun and the moon, and these are causing predictable changes in stress within the ground. Then we have our barometric pressures, and some people working in groundwater engineering would be familiar with using barometric changes and comparing that to your water level changes so that you get a bit of an idea of the confinement of an aquifer system. But we've done a lot of work in this area over many, many years, and one of our recent papers is a review article in Reviews of Geophysics. Tim McMillan is one of my PhD students. And so some of the work that we're continuing to do in this area, where we've been able to turn some of these innovative technologies that are based on the sun and moon, the earth tide effects, into something that's actually really useful. So the kind of changes that we see in the water levels due to earth tides and due to barometric changes are very small. So it could be millimetres, it could be centimetres, and these kind of groundwater level variations are happening perhaps twice a day, roughly, and they're going to be even less in an unconfined aquifer than in a confined aquifer. But if we take the time series measurements, when we've got a logger in there monitoring, say, every hour or every few hours, we take that signal into frequency domain and analyse this for the signals, then we can do a whole bunch of extra value adding to that data that's being collected. So it's kind of like we're getting these really big data sets these days because we tend to start to use more of these automated logging systems. And rather than just telling us how much the water level is going up and down, we can actually now use this as like a ground test technology, or like a mini aquifer test, if you like. And we can do it in an aquitard, we can do it in an aquifer. It's relatively inexpensive compared to a big aquifer pump test where you've got to put a big bore in the ground and you've got to pump lots of water. So we can measure specific storage or how much storage of water's in that formation. We can measure the compressibility of the ground, which we can work out some geotech parameters. We can look at subsidence predictions, for example. We can look at bulk modulus if you're a geotech engineer. We're not going to go into too much of these details now, But it's a pretty exciting set of developments that we've been having over the last few years that really can super value add to the data that's being collected on these very small changes that are happening in groundwater level due to stresses in the ground. So if you'd like to know more, we can certainly talk more later, and some of these publications are available freely to download on ResearchGate, which I'll give you the link at the end. But there's lots of different signals that we can look at that come through, and the frequency in terms of counts per day, and whether they're lunar related or solar related. In fact, some of the most useful that we're finding are these signals, the principal lunar semi-diurnal and the principal solar, roughly 2 counts per day. But when we take it into frequency domain, we can look at all these, and we can analyse in far more detail than I've got time to go into now. The other aspect of this is that the water level can change due to loading at the ground surface. So it might be the filling of a dam, it might be a pile of construction material, and the famous example of a train passing over back in, this is Jacob's work in 1939, and the water level went up just by a centimetre or so for a few minutes, and then slowly the pressure, the water level changes. But the loading and unloading, again, it tells us a lot about an aquifer system, and we can characterise it very well with that. So all these technologies that we have available to help us in designing bore water supply systems, in helping to manage seepage into quarries and mound voids, in looking at injection of water or injection of CO2, carbon sequestration into the subsurface, or whether you're involved in underground tunnelling and mining, there's all sorts of value add that we can do with kind of more advanced pore pressure analysis using these Looney kind of responses. The other thing is, just really briefly, with one quick slide on this, is about water tracer tools. And we've been using fingerprinting techniques with water to also help with water management, and just to verify whether in fact water is flowing along a potential flow path, whether there's high pressure to low pressure, to complement our water models and our empirical predictions. So just one quick slide on this, that we have got a large project funded at the moment by industry, where we're working with ANSTO, Australian Nuclear Science and Technology Organisation, and we're looking at lots of different types of geochemical ions, trace ions, water traces, isotopes, and some emerging new ones to see what are the best options that give us value for money, and depending on the question you've got, can answer questions around or uncertainties that we might have in seepage into tunnels such as these, and where all the rock bolts are forming little conduits for discharge, and how that might propagate up through the system to the surface, or we might be lucky enough to have a good confining unit to form a nice barrier for us between the ground and the surface. So all of this kind of work that we do is really important for helping to design projects well, to manage these water resources well. And I think one of our roles in university is to really do this kind of independent research, to not only develop some new techniques and some new know-how, and to train new engineers in all of these kind of things, but also to get involved in helping industry, whether it be mining company, to optimise the management of their water. I'm also involved in some expert panels for the Federal Minister of Environment and Energy, for example, the IESC, which stands for, let me see if I can, the Independent Expert Scientific Committee for Large Coal Mining and Coal Seam Gas Developments. And so there's a lot of our research and so forth that I think really we like to see the usefulness, I guess, of how this can be put to practical outcomes. And It's really terrific that Deakin environmental engineering has been growing. We've seen a tremendous investment in expanding the environmental engineering program at Deakin. You may be aware that it ran quite a few years ago, and then there was a break, and last year the environmental engineering program was relaunched by our then Vice-Chancellor. And so we've got a really growing number of staff across different areas in soils and water and groundwater, surface water. And in fact, we're now over 80 engineering staff in our school. And you can see the numbers there in environmental engineering. We've got a little hashtag there that we use on social media if you'd like to follow us. So we're really very keen to be involved in engineering projects where we're balancing all of these things between environmental outcomes, economic requirements, considerations to get that balance, and ensure that our built environment, whether it be tunnelling, whether it be mining, how we can ensure that this is not only productive and safe, but it's also sustainable from an environmental point of view. So if you'd like to talk with any of us further about these kind of opportunities to partner, we'd be very pleased to do so. So just to wrap up then, going Looney. I hope I've convinced you that in fact the sun and moon can have an influence on our water levels underground, and not only a small influence perhaps compared to some of the other influences where water levels might go down, up or down by millimetres, metres. We've got a lot of natural factors with rainfall, a lot of human influences like pumping. But even though the sun and moon only affect our groundwater very, very small amount, millimetres, maybe a centimetre or two, if we've got those really sensitive monitoring systems in place, that we can actually put this to good use, and we can actually use these effects to help us with our specific yield, our storage estimates, to help us with compressibility numbers, just like lots of mini aquifer pump tests telling us what our compressibility is in situ, in there in the ground. So lots of useful stuff that we can do. So that's all, folks. Thank you so much for coming along and for watching this webinar and the recording. And if you'd like to take a look at some of the selected research outputs that we've got freely available on ResearchGate from myself and my many colleagues and research students that I'm working with, please take a look there on ResearchGate, and I'm happy to take your questions.
Thank you so much, Wendy. It was really interesting to hear all your knowledge that you've got, obviously, in this field. We will start the discussion in a moment, so now's the time for attendees to write any questions you might have into the question box on the screen and then submit them. We'd love to hear from you. So I've got one question that's come through. So what impact do you see in this research having?
Yeah, that's a good question. Thank you. We definitely like to focus on research that's going to have some kind of useful impact. And the latest research that we're doing, I think this is actually going to be quite transformative. In fact, I was recently at an international groundwater congress, and the reviewer was saying that these kind of techniques, when we lay them out and go into some of the maths and some of the groundwater examples, can be quite transformative, because we can save money by doing lots of these little monitoring points that will enable us to get real measurements of the geotechnical properties and the hydraulic properties of the sediments and of the rock as they are there in the ground, so in situ. The other techniques that we have at the moment in our conventional engineering practice would be to, say, do some geophysical tests, to take some samples, to take some cores back to the laboratory perhaps and do some some rock core testing to get our geotechnical parameters, such as our bulk modulus. We would, in groundwater engineering, we might have to put a big bore into the ground and put in a big pump and pump it for, a couple of days with a big generator on site. And so this is very, very expensive to do this kind of investigation. So our research using the effects of the sun and the moon and other things that we can, if we've got a system that's responding to earth tides and to barometric pressures, and we've got appropriate design of our automated loggers, and they're sensitive enough to pick up these really small changes, then it's really amazing what we can now do to calculate out all of these hydraulic and geotechnical parameters that otherwise would be almost impossible to get, or it would cost a lot of money. We certainly wouldn't get as much data as what we're able to get now. So wherever there's automated loggers already out there, it really enables us to really hugely increase the data that's being collected and the usefulness of that data.
Great. So we've just got a couple more questions that have come through. Another one from Lee. So what is the minimum frequency you would suggest for loggers?
Yes. So this is a really, really important question. The minimum frequency that we need is actually related to the frequencies of the signals that we're actually trying to analyse in frequency domain. And there's certain mathematical rules then about how often you need to sample those in signal analysis. And it turns out, to cut a long story short, that we need at least every 4 hours, okay? So perhaps every hour as well, that would be fine. So 24 measurements a day, and we'd want to do that for ideally 3 or 4 months. All right, to then back out all of these geotech and hydraulic parameters from that data set. But we also want to ensure that we've got an adequate vertical resolution. So it's not just the time resolution or the frequency for the loggers, but there's a few other things to consider as well. But thanks for that question, it's pretty important.
Awesome. So if anyone has some other questions to send through, please do send them through. We've got another one from Mojo. So how the safe yield of aquifers is observed in Australia, looking at unexpected drawdown in GW, how the induced recharge programs are planned.
Yeah, okay. So I think this varies quite a bit depending on which part of Australia that you're in and which jurisdiction. But the safe yield or the sustainable yield of aquifers is often calculated on the basis of using the monitoring data from the groundwater level data and putting it into a numerical model. So putting it into a groundwater flow model, like one of the common software is ModFlow or FeeFlow. And we kind of simulate the rainfall recharge and try and match it up with what we know of the geology and what we know of the groundwater levels going up and down. And that way, the sustainable yield is set in each of the management units. Okay, so in Victoria, we have a number of groundwater management units where there are rules around how much groundwater can be taken out. And so each groundwater user would need to have a license to, firstly, to install a bore, and then a license to access that water. And it may be that year by year, the volumes of water that they're permitted to extract and to pump is changed depending on where things are at. But there's also in some areas of Australia what we call managed aquifer recharge or induced recharge, where there's deliberate attempts to try and put more water down in the ground. So particularly in South Australia, there's many of these managed aquifer recharge projects, and in the Burdekin aquifer on the coast of Queensland. And there's lots of different ways to design these induced recharge programs. But look, it's a great way to store water underground where you're not going to lose it because of evaporation. So there's many parts of the world in drier parts of the Middle East and Africa and India where this is done quite a lot, and in fact was done in historic, in ancient times as well. But I think there's certainly more scope to do this in the future, and we can get smarter by instead of pumping the water out or capturing water from a river and putting it in a surface dam and letting half of it evaporate every summer, we could actually leave it in an aquifer until we really need it, and hopefully put even more down in an aquifer to enable it to recover quickly and to ensure that we're using water in the best way that we can.
Fabulous. So that's all the questions we have time for today. Thank you again, Wendy. So please don't forget to follow Deakin Alumni on our social media channels. We're on Facebook and LinkedIn and would love to hear from you. Also a great way to keep in touch with any events or future webinars that are coming up. We've also got a small reminder that Deakin alumni and their direct families are eligible for 15% off postgraduate course fees. To find out more information about this great offer, just visit the Deakin alumni website, or feel free to give us an email as well at the email address below. We run a number of competitions for alumni throughout the year. We are currently running a Deakin Where in the World competition, and alumni could win a trip to a fabulous mystery destination valued at $6,000. To follow our social media pages if you'd like to get involved, and there's further information in our Deakin Times alumni newsletter. If you don't receive the newsletter, feel free to contact Deakin alumni at deakin.edu.au to make sure we add you to the list. We'd love to stay in touch with you in general. Please make sure we have current contact information for you so we can invite you to relevant events and more. For your postal address allows us to invite you to events in your area, so please be sure to update that as well. And thank you so much for joining us. You can submit any feedback from today's webinar to deakinalumni@deakin.edu.au, and a recording of the presentation will be available on our website in around 3 weeks. Thank you again to our presenter, Professor Wendy Timms, and thank you for tuning in and participating in today's webinar. Enjoy the rest of your afternoon.